building on our orthogonalized procedure, we're going to develop the QR factorization. We're going to be able to show that certain matrices can be written as the product of matrices in special form. Now, in general, matrix factorizations are an important part of computation in linear algebra. They're important mathematically because they provide insight into the structure of matrices, and they're important computationally. They're the basis for several algorithms in linear algebra. Now, notice that a matrix whose columns are mutually orthogonal has a special property. If you take the transpose of this matrix and multiply it by the matrix itself, then you get a matrix whose only non-zero elements are the diagonal elements, and those diagonal elements are the squared norms of the columns. Why is that? Well, let's use one of our definitions of matrix-matrix multiplication. The entry of the product in the first row and the first column is the dot product of the first row of the first matrix times the first column of the second matrix, and so on. The off-diagonal elements are all 0 because these vectors are mutually orthogonal. Now, we can change things around so that instead of getting this diagonal matrix, we get the identity matrix by normalizing the columns. What does normalizing mean? Normalizing a vector means scaling it, multiplying it by a scalar, so as to make its norm 1. And here's the definition of normalize. It just takes a vector and divides it by its norm, which is the square root of its inner product with itself. So, for example, the vector with entries 1, 1, 1, once it's normalized, its norm squared is 1, and the entries are 1 over root 3. Now, if we take these columns and we normalize them, renaming them Q1 through Qn, then we take the transpose of that matrix, multiply it by the matrix. Because the norms of the columns are all 1, the diagonal elements of the product are also all 1. So we see that if the columns of a matrix Q are mutually orthogonal and they all have norm 1, then Q transpose times Q is the identity matrix. Well, we say that vectors that are mutually orthogonal are orthonormal. And if a matrix Q has orthonormal columns, we call Q a column orthogonal matrix. Now, I know it should be called column orthonormal, but that's the way it goes. And if Q is a square matrix and column orthogonal, we call Q an orthogonal matrix. It really should be called an orthonormal matrix, but this is the convention. And we see that if Q is an orthogonal matrix, its inverse is its transpose. We'll learn a little bit more about these orthonormal vectors. Suppose Q1 through Qn are orthonormal vectors. The projection of a vector B onto one of these vectors, say Qj, B parallel, is a scalar multiple sigma j times Qj. And the scalar, sigma j, is the ratio of the inner product of Qj with B by the inner product of Qj with itself. The inner product of Qj with itself is 1 because these vectors all have norm 1. So it's just the inner product of Qj with B. So the vector of these scalars, the vectors sigma 1 through sigma n, can be written using the dot product definition of matrix vector multiplication as sigma 1 through sigma n, which is the dot product of Q1 with B through the dot product of Qn with B. That's the product of this matrix times the vector B. This matrix has as its rows the vectors Q1 through Qn. And the sum of these projections is the linear combination sigma 1 times Q1 plus up to sigma n Qn. Can be written as this matrix, whose columns are the vectors Q1 through Qn, times sigma 1 through sigma n. Now we'll start to develop a procedure for producing the QR factorization. Remember that the result of orthogonalize is this relationship. Here's the matrix whose columns are the original vectors supplied to orthogonalize. Here's the starred versions, and they're related by matrix multiplication with this upper triangular matrix. Now these starred vectors are mutually orthogonal, but they're not orthonormal. So let's assume that the input vectors are linearly independent. In that case, the starred vectors are all non-zero. So we can normalize them. We'll normalize these vectors, replacing them with their normalized versions, and we'll call the normalized versions Q1 through Qn. Now, to maintain this matrix relationship, because we're normalizing these, that means dividing each of these by its norm, we have to multiply the corresponding rows of this matrix by the norms of these vectors. And so we get a slightly different triangular matrix. Instead of ones along the diagonal, it has the norms of the vectors v1 star through vn star. And the other entries are modified as well. This is called the QR factorization of the matrix formed by the original vectors v1 through vn. In this case, the matrix whose columns are q1 through qn is called Q, and the upper triangular matrix is called R.